Good afternoon, dear audience. I'm Chen. It's of my great honor to present with our work, Cross-Layer Design Against Non-Ideal Effects in ReRAM-based Processing in Memory System. Firstly, I'll briefly introduce myself. I'm currently pursuing the PhD degree of Computer Science in Shanghai Jiao Tong University, and my research focuses on in-memory computing, heterogeneous system, and electronic design automation. The presentation is composed of these 4 parts, and will begin with some preliminaries of the ReRAM-based processing memory and its non-ideal effects. Conventional von Neumann computer has been demonstrated suffering from the burden of the frequent data movement for data-intensive applications, like neural-level computing. Processing memory is a novel computing architecture that promisingly breaks the so-called memory wall by enabling the computation inside the memory. The data movement is significantly reduced and thus improves the overall performance and energy efficiency. A popular implementation of PIM is the ReRAM-based processing in memory system. ReRAM is a non-volatile memory that stores data by resistance, and is leveraged to accelerate the vector matrix multiplication in recent works. In brief, for data-intensive applications, the PIM can significantly outperform conventional von Neumann computer for its higher throughput, massive parallelism, and superior energy efficiency. However, the ReRAM-based PIN is still far from practical usage, mainly for the non-ideal effects caused by immature manufacturing. The commonly known non-ideal effects are listed as the programming variation, the rate disturbance, and the stuck at fault. The programming variation, it means the programmed resistance is different from the target resistance. The rate disturbance means the resistance gradually changes after each read operation, and the stuck at fault means the resistance of the cell is stuck and cannot be overwritten. These non-ideal effects will lead to incorrect computing results, and therefore the network inference accuracy is degraded. In order to solve the problem, we propose our solutions. We'll optimize both the circuit and the algorithm to overcome the accuracy degradation caused by non-ideal effects of ReRAM. In the circuit level, we propose a parallel, precise ReRAM programming scheme to alleviate the programming variation and provide a rapid and flexible refresh capability to overcome the rate disturbance. In the algorithm level, we propose an efficient BNN-wide search framework to target the most efficient and robust BNN for ReRAM-based PIN system. With our optimization of these 2 aspects, the performance and the accuracy of the ReRAM-based PIN system is significantly improved, and we believe it will be closer to practical usage. Now, I'll introduce our circuit-level solution, the precise ReRAM programming scheme. Actually, there are some prior works that try to solve the problem as well. There are 2 types, the write-verify scheme and the self-terminated write scheme. The write-verify scheme generates write ports followed by verify ports till the resistance is reached. The drawback is multiple cycles are required, which incurs high latency. For example, the programming of a VGG16 network requires 46 minutes. The self-terminated write scheme only applies a write programming ports till the target resistance is reached. However, prior works only applies it to SLC, and the termination is slow and the hardware overhead is large. Therefore, we develop a parallel, precise self-terminated scheme which is MLC applicable, and most importantly, can reuse the hardware of PIM system to reduce the overhead and leverage the parallelism. We propose a parallel self-terminating write circuit as shown in this figure. It is embedded into the ReRAM-based product and accelerator. That means the area-hungry components, like the ADC, are reused to reduce the overhead, and thus our circuit is actually with negligible overhead. More explicitly, the area is optimized up to 5 times of reduction. Furthermore, our implementation boosts the feedback speed by 2 times, which is very helpful to improve the programming accuracy. As shown in the figures, the programming delay on MLC ReRAM and deployment energy consumption of our scheme can significantly outperform prior works, which is benefited from our circuit reusing and parallel design. Further, we provide a case study of redisturbance. A practical approach to resist the redisturbance is to refresh the stored data periodically. That's to rewrite the cell to calibrate the resistance. However, when the device is being refreshed, it cannot perform computing. Thus, the performance will be decreased. Therefore, it's a trade-off of accuracy and system performance. If you refresh frequently, the rate disturbance is eliminated, but the system will halt more frequently. If you don't refresh, the accuracy will significantly reduced. We perform an exploration to find the balance point. For Resonance 18 on Cyber 10, a decent choice is to refresh after 200 cycles of read, where the refresh latency only takes less than 1%. Or we could choose other points based on the practical requirements. Then, I'll introduce our algorithm level optimization, the high-performance binarized neural network. The BNN is exactly the 1-bit network, where the parameters are 1-bit data rather than float-point data. Why BNN? It's because BNN can simplify the peripherals, minimize the model size, and enhance the tolerance to stack-at-fault error. However, application of BNN is a challenge for the drastic accuracy degradation. Fortunately, recent study shows widening the network could alleviate the accuracy drop, and thus we are motivated. We propose the hardware-aware automated wide search for accurate, energy-efficient, and robust BNN on ReRAM-based product engine, and simultaneously achieves the following objectives. First, similar accuracy with respect to the float-point counterparts. Second, fully binarized computation that can be executed on ReRAM crossbar without any additional computing units for float-point operations. Third, rapid and hardware-aware BNN construction. A BNN with comparable accuracy and minimized energy is obtained via 3 stages. First, SuperNet pre-training, then reinforcement learning-based optimal wide searching, and finally, the architectural training and estimation. In the SuperNet pre-training stage, we'll create and pre-train a binarized SuperNet with reduced cost. The binarization function insertion is to binarize all convolution and linear layers. The batch norm and activation binarization can be fused and performed by comparator without introducing extra float-point units. The topology modification is to remove the average pooling to compensate the accuracy degradation by generating low-dimension features. The two-side regularization solves the problem that is sensitive close to zero with generating opposite outputs after binarization. DDPG-based reinforcement learning algorithm is leveraged to assign the layer-wise expansion ratio to optimize both the accuracy and energy consumption. The DDPG agent makes action to determine the wise configuration in a layer-wise manner, based on the state and reward acquired from the environment. The candidate is evaluated to obtain the accuracy and energy efficiency, and then to return the reward for generating the action in the successive episode. Experiments are conducted to prove the effectiveness of our solution on multiple backbones. The results are listed in the table. While our solution with fully binarized layers achieves decent inference accuracy and low search cost, and most importantly, without any float point operation. Besides, our solution presents greater robustness to stacked fault efforts in ReRAM PIM system. In the last section, I'll give a brief conclusion. We focus on ReRAM-based processing in memory system and the target to overcome the non-ideal effects. Both circuit and algorithm level optimization are proposed to solve different effects. Our parallel precise ReRAM programming scheme could rapidly and precisely program the ReRAM to resist the programming variation. Our novel circuit design greatly enhances the programming speed and reduces the energy consumption, which will benefit the overall performance. And the disturbance is alleviated by refreshing that takes in significant percentage, which is benefited from our rapid and parallel programming scheme as well. An algorithm level, our hardware BNN-wide search framework presents a reliable approach to find a high performance and robust BNN to maximize the accuracy and performance of ReRAM PIM system. That's all of my presentation. Thanks for your listening.